Okay, so here's a short video about a technique of finding antiderivatives called partial fractions. So let's start with, I got two examples that look very similar. As the name implies, partial fractions, you're going to be using this. This isn't possibly a technique you'll use if you're finding the antiderivative of a fraction. And both of these are fractions, but if you look at the first one and think u substitution, if I let u equal the bottom, x squared plus 6x plus 5, and my du is going to be 2x plus 6 times dx. With u substitution, remember, if this is my u, as long as I could somehow make this numerator turn into du, then I wouldn't need to bother with any other technique other than u substitution. And sure enough, we can see here that if I were to just multiply, wish for a 2 in the top, and compensate with a 1/2 on the outside, then the 1/2 stays there. This now becomes, if I distribute that to 2x plus 6 times dx over, let's just call that u, since that's my u. And then I could exchange this in for my du. So this is 1/2 du over u. Remember, your antiderivative of du over u, also known as 1 over u du. That helps me sometimes to think about what function has a derivative of 1 over u times the derivative of u. It's the natural log function. So this would be 1/2 natural log absolute value of u plus c. And if I just replace back my u with x squared plus 6x plus 5, I'm done. Okay, so I wanted to show you that first because before you jump into this other method called partial fractions, which we're going to talk about here, it's important, you're going to see it's a little bit long to do partial fractions, so it's important to check and see if u substitution would work out first. On my next one, it's the same denominator, and we saw that if u sub was going to work, I would need to be able to wish for something, some constant I could put here that would somehow change x plus 2 into 2x plus 6. And you see, that's not going to happen. I can't put one single constant here, but that when I multiply it by x plus 2 is going to change that into 2x plus 6. So this time u sub isn't going to work. If that's the case, then the next thing you're going to look for is to see if the bottom factors, which it does. This is x plus 1 times x plus 5. And the idea behind partial fractions, let's do a little lesson over here. What partial fractions are all about, it's easier to see how this plays out with numbers. When we add fractions, like if I want to add 1/2 plus 1/3, we already know just by the way we add fractions with common denominators, we can already say that that denominator is going to have to be 6. Right? And why 6? It's the product of these two, right? The way we add fractions, you would need to have 6 as your denominator. And if you actually go through and add the fractions, you're going to end up getting 5, 6. What partial fractions is all about is, what if I gave you the answer? Like, what if I said 7/10 and I said, well, I'm thinking of some fractions that would have given me this as a sum. Well, if we use this as a model, we think about, well, what would the denominators have been to give this 7/10? 10 is 2 times 5, so it would make sense that one of the denominators was 2, the other one was 5. And we could figure out what the numerators are so that when I add them, I get 7/10. So what we could do is temporarily call this numerator A, this one B, and then try to figure out what A and B are. So the idea of partial fractions is you're taking a single fraction and you're trying to express it as the sum of 2 or more fractions. This is what's going on. So back to this, here is a single fraction, and our goal now, since we couldn't make it work with u substitution, is to try to think about how we could rewrite this single fraction as the sum of 2 smaller fractions. what would those denominators have been? Well, if we have x plus 2 times x plus 5 as our final denominator, it makes sense that one of these denominators was x plus 1, the other one was x plus 5. And we could temporarily call the numerators a and b, and then we'll try to figure out what a and b are. Okay, so this is my setup. What's going to happen next, I'm going to take a whole nother step here to show this. To solve for a and b, what we want to do is take this equation, and the next thing we're going to do is get rid of the denominators. And so one way to get rid of the denominators, if I multiply this entire, both sides by the lowest common denominator of the whole entire problem, which is x plus 1 times x plus 5. On the left side, we can see that cancels it out, and I'm just left with x plus 2. On the right side, if you distributed this to the first fraction, you'll see that the x plus 1s would have canceled because you have one in the numerator, one in the denominator. So we would have had a times x plus 5. And for the second fraction, the x plus 5s would have canceled, and I would have had b times x plus 1. At this point, there's two different techniques that we could proceed with to try to solve for a and b. The one, I'm going to choose the one that's not in the book. And I think it's easier. I think it's more intuitive of how it works. And your professors shouldn't care which method you use. It doesn't have to be the book's method. Most professors know both of these methods work. They're just picking one to show you, okay? So I think this is easier. This is an equation. And so what I could do with this equation is I could try substituting in some numbers. I'm going to plug in -5 for x. If I plug in -5 for x, -5 plus 2 is -3. And this is why I chose -5. This term's going to be 0. -5 plus 1 is -4b. And so I now have the equation -3 equals -4b. I could divide by -4 and figure out that b is going to have to be 3/4. Once I know b, now I want to solve for a. So I'm going to go back to the same equation. This time I'm going to plug in -1 to everywhere. So -1 plus 2 is 1. -1 plus 5 is 4a. And then this term becomes 0. 1 equals 4a. A has to be 1/4. All right. So the idea is now, remember, we were trying to integrate this single fraction here. We were trying to find the antiderivative, and we couldn't do it. But this single fraction equals the sum of these two smaller fractions with these values in the numerator. So the idea is I'm going to plug a and b back into here, and that's now what I'm going to be integrating. I'm going to be integrating a, which is 1/4 over x plus 1. And you could do this as two separate integrals if you want. Maybe I'll do it that way. And then b is 3/4 over x plus 5. Each of these, okay, hopefully you've got enough practice now with integrals. If you factored out the 1/4 from here, you'd be left with 1 over x plus 1. And the antiderivative of that would be natural log, absolute value. Same thing here. If you took out the 3/4, you'd be left with 1 over x plus 5. That antiderivative is also natural log. And then we just tag on plus c at the end. And that's our antiderivative. Let's do one more. Okay, I've got this fraction to integrate. My first attempt should be at least to think about u sub. If I let u equal the bottom, du in this case is 3x squared minus 1 times dx. Oh, so close. The trouble is in our numerator, we have 3x squared plus 1. And the way it works for the wishing technique, remember, is that I can only wish for a constant that I multiply this whole numerator by and compensate with the reciprocal outside. I can't just like switch that positive one to a negative one. I can't wish for that. That's not allowed. So as close as that looks, this is not going to work. So that leaves me with factoring the bottom. If I take out an x first, that's x squared minus 1. And you should factor it completely. So factoring x squared minus 1, that's a difference of squares, x plus 1 times x minus 1. And then we're going to rewrite this fraction now. We're going to take a break from the integral, and this is where partial fractions comes in. We're going to rewrite 3x squared plus 1 over x times x plus 1, x minus 1. We want to think of all of the possible fractions that could have added up and given me this as a sum. So this time I have to consider 3 denominators, x, x plus 1, x minus 1. So we'll call A, B, and C our numerators. If you do x, if you switch the order here and your A is over that one and your B is over this one, it's all going to work out the same, right? It doesn't matter. So that's going to be my setup. Now what I want to do is get rid of the fractions. So I'm going to multiply both sides by the common denominator of the whole problem, which is x times x plus 1 times x minus 1. X plus 1. Let's make that x plus 1, x minus 1. On the left side, everybody cancels out. On the right side, for the first fraction, the x cancels out. So I have a times x plus 1, x minus 1. For the second fraction, the x plus 1's cancel out. And for the last fraction, it's going to be cx times x plus 1. Okay, so now I'm ready to start substituting values in for x. So I can see 2 nice values right off the bat. If I let x be 0, the left side, 3 times 0 plus 1 is just 1. If x is 0 here and here, I'm going to have a times 1 times negative 1. That's minus a. And because there's a 0 here, this part will be 0, and 0 times this whole thing will be 0. So I really just have zeros for the other two. If 1 equals negative a, then a equals negative 1. Another nice value, if x is 1, 3 times 1 squared plus 1 gives me 4. And so you see how this works. X minus 1 is going to be 0 when x is 1. So if you see that factor, that's going to be 0, that's going to be 0. C times 1 plus 1 is c times 1 times 2. So that's going to be 2c. C is going to be 4 divided by 2 is 2. And the other last nice number is x equals negative 1, which is going to make any factor that has x plus 1 equal to 0. Negative 1 plus 1 is 0. I got to plug it in here, though, first. So that's going to be, still 4. But this will be 0, negative 1, and then negative 1 minus 1 is negative 1 times negative 2. So that'll become 2b. And this factor is going to be 0 for the c term. So that's going to disappear. 4 equals 2b gives me b equals 2. So that's all the hard work, is solving for these constants. Now we're going to put them all right back into these 3 fractions, and that's what we're going to integrate. So we're now integrating negative 1 over x. Ooh, let me slide that up. Plus b is 2 over x plus 1, plus c is 2 over x minus 1. The previous problem, I broke that up into 3 separate integrals, but as long as you're comfortable, the integral of the first one's going to be negative ln absolute value of x. This one's another ln. It's 2 natural log of x plus 1, absolute value, and then another 2. You get a lot of ln integrals when you do this. So oftentimes you can just go straight to integrating without separating those out. I like to joke here, after we found our antiderivative, technically we would put plus c, but I kind of joke here because c is already used up, right? We've already got c as equaling 2 here. So, you know, I like to joke, we put c just to represent some constant. And nobody's going to mark you down if you put plus c, but you know, hey, we've already used that. So, you know, sometimes if you just make your teacher happy and smile, you know, they might like be in a better mood when they grade your paper. So maybe instead of plus c, we'll put happy face here, and we'll just say happy face is a constant. That was constant, that's c. Okay. So anyhow, that's partial fractions. If you have friends in the other series, particularly 21B, they do partial fractions too, but these can get worse. They do some different kinds of fractions. Our book doesn't have anything worse than what we've just done in these last two examples.